am Dan Krotz with Berkeley Lab's Communications Department, and we're presenting this lecture series. Over the next several weeks, 6 eminent Berkeley Lab scientists will discuss several major scientific advances and milestones conducted at Berkeley Lab during its 75-year history. Today, to kick things off, we'll hear from Dr. Richard Muller, who is a physicist who holds joint appointments with Berkeley Lab's Physics Division and UC Berkeley's Physics Department. Dr. Muller began his career as a graduate student at UC Berkeley under Nobel laureate Luis Alvarez. He conducted particle physics experiments and worked with bubble chambers. He received his PhD in physics in 1969 and joined Berkeley Lab in 1975. Muller also won a Genius Award from the MacArthur Foundation in 1982. Since then, his work has encompassed a wide range of interests, including understanding the ice ages, the dynamics of the Earth's core mantle boundary, patterns of extinction and biodiversity through time, and the processes associated with impact cratering. Please join me in welcoming Dr. Richard Muller.
Thank you. Thank you all very much. It's sort of astonishing to listen to the introduction, and he talks about the 75-year history of LBL. And I look up there, and I'm talking about what's happened over the last 27 years, and that's more than a third of it. And it just seems astonishing to me that 1/3 of the period had one of the most exciting developments of that last 1/3 of this history had something that was so far away from the people who envisioned what this laboratory would be, was so much out of the box that my jaw still drops from this. And it's one of the things I've always loved about LBL, that we're a bunch of scientists, and we could follow where the science leads us. And that's one of the most exciting things about this place, and I think it's one of the great triumphs. There are very few places in the world doing elementary particle physics which could have become the center of the story about what killed the dinosaurs. And that's what LBL became. It started 27 years ago, dinosaur extinctions. 27 years later, no, the dinosaurs didn't go extinct 27 years later. This is 27 years after the LBL team. It was Luis Alvarez, his son Walter Alvarez, Frank Asaro. Frank, are you here? Frank? He lives right next door. He must have forgotten about this. And Helen Michael. And they just broke the whole thing wide open. This is a team that had no credentials in this business. Well, Walter Alvarez had some credentials. He was a geologist. And he got the whole thing started in his studies in Gubbio, Italy, where he was looking at layered rocks. I'll be showing you that in just a moment. And he found this intriguing layer. And within a few years, I'll briefly go over that story because the story hasn't ended yet. It's been 27 years of ongoing research. This thing broke open. Now, a lot of you are too young to remember what it was like before Luis Alvarez and Walter and Frank broke this thing wide open. But I was interested in dinosaurs when I was a kid. And I went to the library to get out books on dinosaurs, and I got out both of them. I read them both. And I love this stuff. I was thinking of becoming a paleontologist until I read the second book. I discovered what paleontologists do is they crawl on their bellies and they scrape away rock, and it sounded awful. So Stephen Jay Gould says he's every kid loves dinosaurs. He was the only one who actually became a paleontologist. Anyway, I would like to point out that if you look at the history of the popular interest in dinosaurs, it was the Alvarez LBL team that broke this thing wide open. This story hit the headlines. It became famous. It became controversial. The controversy didn't last as long as most people think it did, because people who don't know much can sometimes get headlines by contradicting what everybody else thinks. So it was kept as, in the press, it was controversial for much longer than it was actually scientifically controversial. But as I remember that period, suddenly dinosaur movies started appearing, impact movies started appearing, books on dinosaurs. This whole thing exploded. We got Barney, all sorts of things. I always thought that the LBL should have benefited from this. 1% commission on everything dinosaurs, and then we wouldn't need Department of Energy funding or anything. It would just all be carried that way. But anyway, this happened 27 years ago, and a lot has happened in that subsequent period. So there's Luis Alvarez, who was my PhD advisor. He started working on this stuff because he wanted to work with his son. His son was doing geology. His son had actually discovered this thin layer here. And this was a few years later when Louis went to visit this. And Walter looked at this with a microscope. And he found something very peculiar about that layer. And he got really interested. He went and told his dad, who was a physicist, who had no idea why his son liked this boring subject of geology. I'm absolutely serious about that. And he was curious enough, so, okay, show me something interesting. So Walter said, well, there's something very interesting about this layer. And I'll come to that in just a moment. It turns out that this layer here, that thin crack where they're putting their hands, was the key to understanding and unraveling the entire story of what killed the dinosaurs, which has much larger implications for the history of life on Earth and maybe in the universe. So it was just a fantastic thing. Here's my bottom line. I'm going to end the talk with the same thing. They discovered 27 years ago what killed the dinosaurs. Since then, we have learned a lot. However, there's a lot more we don't know now than we didn't know 27 years ago. Okay. In science, that's what we consider progress. And I think that's true. The history of LBL is there's so much more now we don't know thanks to LBL than when LBL was created. Okay. So let me get back into a little bit of geology, because this is a very interdisciplinary, cross-disciplinary field. And that's, I think, the only reason this work wasn't done 50 years earlier. This is work that doesn't fall into any neat category. There was no department of asteroids killing dinosaurs in any university. This is an area that required a geologist, a chemist, two chemists, and a physicist working together, a physicist who not only knew nuclear physics, but he also knew astrophysics, because this could have been discovered 50 years earlier, and it wasn't. 1812, geology isn't actually that old a science. Here we have layers of rock. These we now know, Cuvier figured this out, they were laid down on the seafloor as fossils, and mostly microscopic fossils, fall down on the bottom of the sea. They leave a layer, and the layers build up. And after millions of years, you get these layers of rock. Sometimes when there's mountain building, these layers will then push themselves up. But they leave a record of the history of life. Because in these rock layers, you get the fossils. So you can see what the fossils were like a long time ago or in the more recent past, and you get this evolution. If you've been to the Grand Canyon, you know this. These layers are like a tape recording of the history of life. It recorded elements of the climate, of how many glaciers there were. This is another subject I've gotten into. So here's this wonderful history in geology that you can read with a magnifying glass. And this is what Walter had looked at. So here we have two pictures. There's the one I showed you a moment ago. Walter had looked at this. Here's me when I was visiting this is 1985, so this was 6 years later. You'll notice the change in the rock. Here it's a very thin layer. Here it's completely eroded. Don't shout out the answer, but you know why? The reason is basically tourists. Basically, this location became so famous worldwide, not so much among the general public, but among scientists, that any scientist who was remotely interested in this field visited the site and took some samples back. And here's the gap that was left. I brought some samples too. Anyway, here we see the layers of rock. They were once under the ocean. This layer now, we know, was formed 65 million years ago. They were under the ocean, but because of mountain building processes, basically from plate tectonics, these things came up above the ocean. They were tilted, as you could see, as this big mountain was forming. And in fact, the reason it's clear right here is only because they built a road. people teased Walter Alvarez that he's a roadside geologist. Because he went by the road here and he was studying this layer, and you notice it's sort of white down here and then it changes color, and he became really intrigued with this layer. So what he showed his dad was a little sample of rock that he had brought back. Here's the rock below the layer. There's the layer, which had a lot of clay in it, and the upper layer. And he looked at this, typical geologist will spit on it and then look at it with a magnifying glass. And when he looked at it, this is what he saw under the magnifying glass. These are animals called foraminifera. They're single-celled animals. These are actually fairly large, maybe a millimeter in size. And here they're all gone. There are a few foraminifera left, but just little ones. Most of the species of foraminifera disappeared at that moment. Now, Walter knew this was about approximately, within 5 million years, the same time the dinosaurs disappeared. And he speculated that maybe these events were simultaneous. He brought this rock to his dad and said, what can we do to figure out exactly how old this is, how long this layer took to be laid down, and so on. And Louis went to his nuclear physics books. And after rejecting dozens of ideas, this is a part of science that usually isn't described, all the wrong ideas that he rejected as not working, he finally decided that the key element to understanding this is the element iridium. And then he contacted Frank Asaro because he knew Frank had the best system, nuclear physics system, for detecting rare elements, and iridium looked like a good one for neutron activation analysis. So they began a collaboration with Frank Asaro and Helen Michael to study the iridium in this layer and use this to elucidate what happened at that time. So let me give you the final picture. There were some false tracks. There were things, there were surprises. Initially, all they wanted to do was to say, was this thing laid down in a period of 1 million years, or was it laid down in 2 million? How long did it take this layer to form? We now believe the answer was just a few days. And that came as a surprise. The iridium proved to be the key. I have so much to say that I'm not going to go into that in a whole lot of detail. Let me just point out why he chose iridium. Here I have an image of a little asteroid. That's actually Gaspra, which is an existing asteroid that's been photographed from a satellite. I just stuck it in up there. An object the size of Gaspra, if it hits the Earth, leaves a signature that can be detected with the element iridium. The reason is that the Earth it was formed from elements from the sun. The lighter elements, like hydrogen and helium, left because they weren't tightly bound enough gravitationally. Some of the hydrogen remains in the form of water. During the molten period of the Earth, much of the iron, not all of it, but most of it, sunk to the core. And so this is where the iron is. Iridium is what's called a siderophile element, literally means iron-loving. And so the iridium of the Earth is mostly in the core. There's not much left on the crust. So the crust of the Earth is depleted in solar system iridium. But small asteroids, comets and asteroids, which were not big enough to be hot enough to melt, did not differentiate, and even if they did, they have all their iridium with them. When this thing hits the surface, it will explode, as I'll show in a moment. And when it explodes, it scatters its material all over. Now, some of that material, like iron, is sufficiently abundant on the crust of the Earth that you really can't tell anything from it. But the iridium becomes a signature of an extraterrestrial impact. So that is what they found in the layer, the excess iridium, and it took them some trouble. The asteroid, it might have been a comet. We didn't know. We knew it was something from the solar system that was small. And based on the iridium, I say we, I didn't mean me, I mean Louis and Walter and Frank. At the time they were doing this, I was a postdoc. I was working with Louis, and I watched him do this sort of stuff, and he kept on telling me about what he was doing, and almost sort of offered to, gee, if I wanted to get involved, that would be great. And I was too smart to get involved because I could tell he was really wasting his time. I mean, he just wanted to work with his son, and this was going nowhere. And so I went and did my own projects, which paid off, it turns out. But I, setting up a supernova search program and a couple other things. But anyway, he was wasting his time on this. But that little bit of iridium was part of it. Now, here's a little bit of hard-level physics. I'll get to some entertainment in a moment, but right now some physics. This is a question of, you have this rock, and it's rock and ice and who knows what else, but basically solid material, and it hits the Earth, and this thing explodes. Not made out of TNT, it's probably made out of silicon and oxygen and iron and things like that. So why did it explode? So let me do a little bit of physics here. So, kinetic energy, as you know, is approximately 1/2 mv squared. Now, the velocity of which things are coming in, the typical velocity, the Earth is going around the sun at 30 kilometers per second. You can get that just by the distance 2 pi around. It takes a year to go. Average velocity of the Earth is 30 kilometers per second. So if you have a rock that's going at 30 kilometers per second, how much kinetic energy does it have? It's just 1/2 mv squared. Divide by m to get the energy per gram. That's just 1/2 v squared. Plug in the numbers, and you find you get 4 times 10 to the 5th joules per gram. That's about 10 to the 5th calories. Or if we talk in terms of food calories, it's 100 calories per gram. Now, you may know that fat is typically 5 or 10. Chocolate chip cookies are 5 food calories per gram. You may not know how many food calories per gram there are in TNT. This high explosive TNT is actually about 1 food calorie per gram, much less than fat. That's why we eat fat instead of TNT. TNT is useful not because it has a lot of energy, because it doesn't. Gasoline has 10 to 15 times as much energy per gram as TNT, but TNT doesn't need oxygen. And it releases this energy very rapidly, so if you want to shatter something, that's what you need. So that's why we use TNT. Anyway, so just to compare the kinetic energy of this asteroid to TNT, it's about 100 times greater. Now, when this thing flies into the Earth, big thing, but the Earth is even bigger. And if you want to make a comparison, just think about a mosquito or something like that hitting a Mack truck. And it doesn't really deflect the truck. It just makes a mess on the windshield. And that's what happens here. So this thing doesn't deflect the orbit of the Earth. It's too small for that. But there's so much energy that this thing is stopped. That energy is turned into heat. What is an explosion? An explosion is when energy for a solid object is turned into a large amount of heat. And so it becomes a gas. The gas is highly compressed because it has the density of the rock. And so it explodes. Explosion is simply the conversion of this much matter into a gas. So that's why it exploded. The story that's 27 years old, it took the world a while to convince themselves that this discovery was right. They had to look around and discover there was not a whole lot of iridium elsewhere. There was a competing theory about volcanic eruptions killing the dinosaurs, and maybe the volcanic eruptions were responsible for bringing iridium from deep down in the core of the Earth onto the outside. Now, there was actually a good reason for that controversy. It seems that it could be ruled out, and those of us who really study this subject, I got involved into it soon after the discovery was made, were really convinced that the volcanic eruption theory could be ruled out. But there were some funny things about the volcanic eruptions that continued to bug us for many, many years afterwards, and I'll be getting back to that. One of the things that ruled out the volcanic eruption was the discovery of shock quartz. Long story behind this, but basically only in explosions do you get quartz that has this kind of configuration. In fact, even little explosions like Krakatoa wouldn't do it. You need either atomic bombs or impacts of asteroids on the Earth. There are these things called microtectites, which are basically the little glass droplets that are made from the vapor of the exploded rock. As this vapor comes out, it begins to cool off and condense. It forms little droplets of glass. We'll come back to these later. I'll show you some glass droplets from the moon that we study to follow up on this program. And these things come down, and they're a fairly good indicator of an impact, just as iridium and shock quartz. And so the story began to fit together. Enough heavy science for a moment. Besides creating an industry of Dinosaurs for Children. The discovery of Alvarez and Asaro opened up a whole new genre of art. And I've actually been collecting this electronically over the years, and I thought I'd just very quickly go through some of the art that it has inspired. This is you'll recognize these images because you've seen many of them. You see them almost every time. So this is one of my favorites. This is by John Dawson. The only thing he got wrong here, by the way, these art pictures frequently have a Tyrannosaurus Rex looking over his shoulder at this big explosion. But they often totally underestimate the explosion. And here we have an object the size of San Francisco carrying energy as if it was made out of, we're talking about teratons of TNT. This is 100 times greater than if you took the whole Soviet arsenal, the US arsenal of nuclear weapons before we started reducing them and explode them all at one place at one time, would still be 100 times less than the energy released by this thing. So, I mean, that's not even one nuclear explosion. So it's very hard. Scientists say, how do you imagine things like that? And I'm not sure we can. I think what we can do is we can calculate. And you calculate what happens and calculate the results, and what happened here, well, let me show you some of the other art, and we'll come back to what it was like. So, there's another painting. Didn't greatly underestimate. This was the cover of Time magazine. This is interesting because this gives you an idea that there's some reason to think that the asteroid may not have been alone. It may have, in fact, been a comet instead of an asteroid. It may have been part of a comet shower. So I'll be coming back to that in a moment, talking more about that. This one gets it a little bit. You see it's left a hole in the atmosphere. Because, I mean, this thing is estimated to be about 10 kilometers in size. And, 1/E depth of the atmosphere is about 6 kilometers or so. It would hardly notice the atmosphere. In fact, we now know that it landed in the water. And the consequences of this are interesting to try to calculate. And there's been a lot of work done on that, a lot of conferences. Here's some more of the art. This one's getting the picture a little bit better, but even so, that, in a nuclear explosion, you can't look around because it's too bright. And this is far greater than a nuclear explosion. In fact, I'll show you some pictures in a moment of a small impact on the surface of Jupiter. The amount of art is amazing. This one avoids the issue by showing it well, I guess it's just impacting there. That's really an underestimate of the asteroid size. This one I like because the dark star actually referred to a theory of mine called the Nemesis Theory that I'll mention briefly. And so here's a children's book that has the featured scientist being me. But here's one of my favorites. No doubt about it, an asteroid killed the dinosaurs. In fact, many people thought that when you get to this iridium layer, you should find zillions of dinosaur bones. But the fact is, dinosaur bones are quite rare. There are fewer than, I think there are about 6 or 8, what are called articulated skeletons of Tyrannosaurus Rex. That's where you find them laid out, as opposed to scattered by the wind and the rivers and the rain. So there really are not many fossils, many fossils remaining. And the dinosaurs are the rare ones. Most of the life that went extinct were these microscopic animals. Most mammals went extinct too. In fact, what we now know is that most animals, period, were killed. People think, oh, how did the crocodile survive? How did the birds survive? How did the mammals survive? Most of them didn't. Imagine that what happened is this thing comes and it hits. You get this huge explosion. What happens? It spreads It spreads rock all around the world. In fact, the layer of rock a centimeter thick has been found in over 100 locations all the way around the world, buried at this depth now because of rock that laid on top of it. The energy release is enormous. The fire rains down. There have been firestorms, evidence of firestorms from the carbon found all around the Earth. Imagine that 99.9% of any one species, 99.9%, are killed off. Almost all of the crocodiles, almost all of the birds, almost all of the mammals, but all of the dinosaurs. At least enough of them that they could not find each other to mate after the sun came back out. So, it doesn't take much. Walter Alvarez once wrote a wonderful little musical song about the mammals. And most of them are dead. And a few of them survive, and it's miserable out. There's dust everywhere, and everything's burned and so on. And a few plants start popping up. And they go and they eat the plants. A little musical ditty that was really lovely. And then there's some fruit on some of the plants, and they eat those, and they make it through, and he finds a mate, because someone else survived. And there they are enjoying their life, this miserable life, and one of them sort of says to the other, honey, I haven't seen any dinosaurs lately, have you? They're gone. And his music then is about the joy when they realize the dinosaurs are all gone. But at that point, it's like rabbits in Australia. One mating pair with no natural enemies, boom! Within 100 years, you've covered the whole Earth. So this is the way life recovered. Not because all the mammals survived, most of them were killed, but enough of them survived. Nothing larger than a few kilograms survived. But the little creatures, if you had enough of them, if they could hide, if they could survive on eating seeds like the birds did, then they could come back and repopulate an Earth that had no dinosaurs. A few more dinosaur pictures here. I like this one because it's one that depicts the wave coming in from the ocean, and these guys are standing around wondering what that roaring sound is. A tidal wave inundated Texas. In fact, that turned out to be a key role in the discovery of the crater, was evidence that a huge tidal wave 65 million years ago came over Texas. This next picture is one of my favorites. See, there's so many people doing Tyrannosaurus rexes looking over their shoulders at explosions that the artist required a little bit more imagination. I don't know whether he's screaming in terror or going, whee! Dale Russell was one of the paleontologists. Not all paleontologists opposed the theory. Some of them said, the dinosaurs didn't go out suddenly. It went out over a million years. In fact, there are two paleontologists. There's what's called the signal ellipse effect, named after paleontologists who said, look, the fact that all these animals were disappearing over a million years doesn't mean they were really disappearing over a million years. It just looks that way. If your last Tyrannosaurus rex is right here, and then you have a meter of rock, and here's the iridium layer, it doesn't mean that's when the last Tyrannosaurus rex disappeared. After when was the previous one? Well, that's down there. So if you take the last creature, it'll always precede the boundary. And then as time goes on, as you find more and more fossils, they begin to approach the boundary like a limit. And that's what's been found with most of the animals over the subsequent 27 years, is that these things that people said went extinct ahead of time, no, you find more fossils closer and closer. It's called the signal ellipse effect. Another paleontologist, Dale Russell, believed that the dinosaurs were such robust, they were the most intelligent creatures that had existed up to that point. And these days, every kid knows that. When I was a kid, I learned that they were dumb, that they went extinct because they weren't smart enough to fend off the little mammals that were eating their eggs. These days, you watch the movie Jurassic Park, and you know dinosaurs were smart. But back at this time, in 1980, 1981, Dale Russell was making this point, saying the dinosaurs had been around for 250 million years, I guess over 180 million years, and they had been very successful. They were the most intelligent creatures, and they would have continued to evolve, he believes. And he came up with this wonderful portrayal of what the dinosaur of today would have looked like if this thing hadn't killed them off. So here I would be lecturing to you about the event that that almost killed us all off, and that's what I would look like. Now, take a look at this thing and try to imagine. This is about the size of San Francisco. So this is Gaspra, and I'll superimpose on it to scale a map of San Francisco to give you an idea of how big it was. And so there's art of this too. I'll go through this quickly. It's not quite as exciting as dinosaurs reacting. But you see, it's another genre of art. This wasn't really that big. Movies, of course. Then a comet. This is just a 1 kilometer comet, not 10 kilometers, 1 kilometer, hit Jupiter. And many of us got to watch this back in 1994. It's sort of an exciting thing to watch. And this is one of the images taken of that. You get some idea of how big. This was 1 kilometer. The one that hit the Earth was 10 kilometers, which was 1,000 times bigger. I wrote a book on this subject, which is called Nemesis in 1988, and I'm rather proud that my cover of my book showed something that was much more realistic than any of the other art. Where was the crater? For 12 years, we didn't know, and in fact, Luis Alvarez decided we will probably never know. There was this tiny crater in Arizona, which you can go visit. It's 1 kilometer in size, but the impactor was 10 kilometers. And typically, when you make a crater, it is 10 times larger than the impactor. So you'd expect a 100-kilometer or several 100-kilometer crater, and this thing was way too small. Here's a larger crater, 45 miles in diameter. We can see it now from space only because they built a dam, and so we get this ring. The center of the crater, when the crater is really deep, the forces within the Earth are so great, they fill up the crater. So you wind up getting only this ring. But this is now known. You can verify this by looking at the rock, looking at the fractures of the rock and the kind of the rock, and this is an impact crater. There are over 100 impact craters known around the Earth. I think I only have 88 plotted here. Walter likes to point out, if you look at the distribution of where the impact craters are, they follow the distribution of geologists who study impact craters. He also points out that if you look in the Bay Area and plot the geology faculty and where they live, it's a pretty good marker of the Hayward Fault. And of course, the reason for this is geologists like to live where it's interesting, where there's some rocks showing. Anyway, so where is the crater? Louis' answer was, we'll never find it. Why? It was subducted by plate tectonics. Here we have the Earth. This is a reconstruction, a whole interesting science. There's a whole field of science to reconstruct how, so this one replays. We had this Gondwana 600 million years ago. It broke up. New oceans were formed. The Atlantic Ocean formed. But you notice on the other side, which this doesn't show, the Pacific Ocean is disappearing. And about 1/3 of the ocean disappeared since 65 million years ago. So Alvarez's answer, well, maybe we'll never find the crater. There's a 30% chance that it was subducted and no longer exists. Well, fortunately, that turned out to be wrong. The crater was found. There it is in this little town of Chicxulub on the Yucatan Peninsula. It's a whole history and a story about the finding of this crater. We should have known back in 1981, but in fact it wasn't identified until the tidal effects, the tidal wave effects, were found in 1991. But that's where it was. It actually impacted right about there. So this is the Yucatan Peninsula in Mexico. And the effects of it can actually be seen in some other satellite photos. Some of them are quite indirect. This, for example, is a change in the geology that we believe reflects the crater. If you measure the gravity by flying above the crater, there are these gravity plots, and just where you draw this line, I think the 180-kilometer line is an accurate reflection of the crater. But Hildebrand and Sharpton seem to think that maybe this is a better one. But it's something like a couple 100 kilometers across. And it was been dated at the right time and so on. Let me shoot ahead. At 1984, some more paleontologists, a distinguished paleontologist, Ralph and Sapkowski, published another rather remarkable result. They had the best record ever obtained of similar things happening, things going extinct. And here's a plot that I made based on their data, based on their paper, of the history. This is 250 million years ago. Here's the present. These are the extinctions. This is an extinction rate. This is the great Permian-Triassic extinctions that took place 250 million years ago, still unexplained, by the way, despite what you read in the newspapers. There's another one here that they noticed. It seemed very broad, but that's because of an uncertainty in the age of this. So there's one there. What they noticed was that these seemed to line up every 26 million years. Nothing there and there, but there seemed to be peaks every 26 million years, and they concluded that this was statistically significant. There was a rush to try to explain it. They were unable to explain it. Mark Davis, Pete Hutt, and I myself came up with an explanation for what's called the Nemesis Theory, and it was quite famous at the time. It postulates that there's a sun orbiting another star orbiting the sun. They're actually co-orbiting each other. But the numbers all work out. Once you postulate that there's something there with a 26 million year orbit, then it turns out that it will have enough an effect on the comets to perturb their orbits and bring in about 1 billion comets into the inner solar system on every close passage. And if you have 1 billion coming in, typically 1 or 2 will hit in what we call a comet shower or a comet storm. So all you have to do is postulate that the sun has a companion star. The rest of the numbers work out. If this has an orbit of 26 million years, then it would happen every 26 million years. It would explain the Raupen-Sapkowski data. There was a little bit of art that grew up around that. Here's the dinosaur enjoying the comet shower. Those aren't impacting. Those are just in space. Only 1 or 2 or 3 of them will impact over a period of about 1 million years. So we had this postulate. One of the famous paleontologists at that time had dinner with Walter Alvarez, Gene Shoemaker. He was deep into this business, and they discussed what they called Rich's star. That's me, Rich's star. Nemesis was my name for the star. And so they were Walter tells me they were discussing this. And then at the end of the dinner, it was a Chinese restaurant in Berkeley. They got fortune cookies, and Walter opened up his fortune cookie. Now, that's not considered scientific evidence, but it's given me heart. You know, now it's been 21 years since Nemesis Theory was published, and it hasn't been discovered yet. We had a program to look for it, and I had a graduate student who thought he'd take this on. He was willing to take on these weird projects, and he worked at it. We were only able to eliminate about 1/3 of the stars that were candidates, but it was enough to earn him a PhD thesis. His name was Saul Perlmutter. And for those of you who don't react, he's the fellow here at LBL who discovered that the universe is accelerating. So this was his PhD thesis, looking for Nemesis. Didn't find it, or he would be famous today. So, very quickly, what have we learned in the last 27 years since time has gone on? It's really interesting, and I'm going to do this very quickly because it's an industry. There are a lot of people working on this. It's an enormous amount that we've learned. Here is the plot, the Raupen-Sapkowski plot of the extinctions. What about these other extinctions? Well, let's just go over them one at a time. That's what I put a little dinosaur there. Let me get rid of the dinosaur. Just to indicate that this is the extinction when the dinosaurs die. That's 65 million years ago. Okay, and this is something about 35 million years ago. Another iridium layer was found by Francesaro. There were maybe 2 peaks. Moreover, there are several layers of microtectites, these little splash things that indicate. So it looked like about 35 million years ago there were maybe a comet shower. And in fact, Alvarez and Shoemaker published a paper saying there was a comet shower at that time. And so that's right there at that time for that extinction. Now here's another maybe 2 layers of iridium that were found at about 91 million years ago. On the plot, that falls right there. Okay, so this one dropped in. There's an iridium anomaly found there. Another one found there, beginning to look like a pattern. Known Earth craters. Now, there are lots of craters. A lot of them are small. Things are hitting the Earth all the time. Let's just look at the big ones. These are the biggest ones. Some of these occurred so long ago that there are no fossils left to figure out whether they killed off any life. So let's ignore the ones that are that old and go to our period. These are the 4 largest craters remaining. This one is the one I showed you in the Yucatan. And that, of course, we know falls right there. Manicouagan, which I showed you earlier, turns out it falls right there. Papagai in Siberia, kind of hard to see there, but it's verified as being an impact crater, very large impact crater. That's right there. Chesapeake Bay, you may not have realized, is an impact crater. It's largely buried, but you could look at the shatter cones of the rock from the impact and determine this was an impact crater. And that falls right there, right at the time when we say there was a comet shower, multiple impacts hitting. So the picture is really getting very interesting. Now this messes it up a little bit. This is one of the great lava flows of all time, the Deccan Traps, they call them, of India. These are layers of flow of lava, and it's a huge area. If you're familiar with how big India is, these are the Deccan lava flows, the so-called Deccan Traps. If you're not familiar with how big India is, let me put California on top of it to show you how large this region is. Well, it turns out the Deccan flow occurred 65 million years ago. It was the biggest flow in this whole period. For 100 million years, it's the biggest flow. It just happened to occur when the dinosaurs died. Isn't that a funny coincidence? Well, this is why there was so much controversy. In fact, the Siberian traps also happened to be the biggest flow in this period, and they occurred right about the time of the Permian-Triassic extinctions. The biggest flow of all time was right here, the Ontong Java Plateau, and there's not much of a peak there. But it was enough to intrigue people. Are all extinctions due to impacts? There's some evidence from the Iridium. At least several of them are, maybe 2 or 3. But what about those volcanic eruptions? Could an impact cause volcanic eruption? This is something I worked on starting in 1984. And every few months, I try to figure out some way to do it. Walter worked on it too. Sometimes we worked together. Sometimes we worked alone. How could an impact cause a volcanic eruption? There are lots of ideas that come to mind. You scrape up the surface, that makes a weak point, and volcanoes start erupting. No. When you look at it in detail, it's self-healing. So we spent a lot of time looking at that. This is the Apollo 14 site. This was an intriguing idea I had. That's Alan Shepard, 2 miles from Cone Crater. At Cone Crater, he collected some samples that we then used in a project we did up here at LBL to try to see whether there was evidence that the moon was being subjected to periodic impacts. I said I'd show you some pictures of little microspherules from impacts. Well, there is one. This one's from the moon, however. We had moon dust up here that we would analyze. The idea being the following. If you get 1 gram of lunar soil, it has these little droplets from an impact. It has droplets from many impacts. In fact, we were able to show that 1 gram of lunar soil had over 100 droplets, mostly of different impacts. By collaborating with the Berkeley Geochronology Center, we could date the time of those impacts by looking at the amount of argon that had accumulated in these glass droplets since they were formed. The argon comes from the radioactive decay of potassium-40. And once it's a liquid, the argon gas leaves. When it solidifies, the argon begins to accumulate. And based on that, we can measure how old these were. So here's a distribution, a plot of the ages. We'd hoped to see a 26 million year period in this. Verify the Nemesis theory, but we didn't have enough resolution. We did see this big increase in the recent past, which is still somewhat, it's statistically significant, but it was mysterious. And I published a paper analyzing that in terms of the Nemesis theory, with a change in the orbit of Nemesis taking place about 400 million years ago. That would account for it. And this is a fairly likely event. I don't want to say much more about Nemesis because all of this postulation, all of this theory is going to become irrelevant. In the next few years, an ongoing program called Pan-STARRS in Hawaii is going to either discover Nemesis or prove it's not there. It's ironic that if there's a star orbiting the sun, we wouldn't have found it, even though it's so close. And that's because most stars are, the most populous kind of star in the Milky Way is a red dwarf. A red dwarf, if it's a light year away, wouldn't be a particularly bright star. We wouldn't notice it because it's moving with us through the galaxy. oh yes, it's orbiting us, but at that point it's going so slowly we wouldn't see any significant proper motion. Anyway, that's the whole Nemesis story, but it will be answered in the next 5 years or so by these survey instruments. There's another one that may go called the Large Synoptic Space Telescope, Survey Telescope. And these things will find Nemesis if we do have a companion star that is orbiting the sun, then we'll know. Soon. What about the Permian-Triassic? I mentioned the Deccan traps. Questions. There are things we don't know. How could the Deccan traps in the Siberia, how could they be caused by an impact? My time is running short. I want to have some time for questions, so let me go quickly. A lot of people point out that the Deccan traps are exactly opposite from where Chicxulub is on the globe. So maybe it set up a big seismic wave that went around the Earth and focused on the other side, or something like that. Walter and I get letters about that typically once every few months, and we always give them the same answer. If you look back 65 million years ago to where India was, it wasn't on the opposite side. It's on the opposite side now, but it wasn't back then. So the antipode or antipodes theory doesn't really work. This was an interesting thing I came up with finally, and I actually published this in a paper, and it really does work. If the asteroid, instead of hitting straight down, hits at an angle, then the outside of the Earth starts spinning. This is a liquid core. It will spin like as if you take a wheel that's on an axle and you give the outside a spin. It doesn't drag the inside part around right away. That puts a shear across this, which affects the temperature distribution. And it's rather straightforward calculations show that this could cause a change in the temperature distribution right here that could cause an upwelling to flow. So as far as I know, this is the only published theory where the numbers really do work out that shows an impact on the surface could cause an upwelling to come from in here that could in fact cause the large volcanic eruptions known as the Deccan traps or the Siberian traps. So I think I have a little depiction of that right here. Boom. Okay. Now, as soon as I came up with this theory, I realized that it would have another consequence because the Earth's magnetism comes from this region in here. This liquid core creates the Earth's magnetism, and this would disrupt the liquid core as much as it would everything else. And I thought it would disrupt the Earth's magnetism. If you disrupt the Earth's magnetism, eventually the Earth's magnetism will restore itself, and you'll get the dipole back, but there should be a magnetic reversal. So this is when an impact could trigger magnetic reversal. And just very quickly, there was this period, the quiet period, when there were no reversals. And I thought, hey, I can explain that. If there were a giant impact right here, if there were a big impact right there, then there would be so much of an avalanche of the core mantle boundary that there would be no longer any mechanism for creating reversals until the little mountains at the core mantle boundary had a chance to build up. Don't have time to go into that in a lot, but then you'd have this gradual increase. So I had a neat explanation for this. The only trouble was, if that were the case, there would have had to have been a giant volcanic eruption at this time. So I went to my table of giant volcanic outflowings to look at this period 120 million years ago. Nothing. So what do? Publish anyway. But in science, you have to show your dirty laundry. So here is the paper. I highlighted in red. In the publication, it wasn't in red. I highlighted in red. However, we also expect to be able to observe a consequence of the event which started the quiet period. We might expect there to be a large plume, basaltic flow, near the beginning of this period, or at least evidence of a large cometary impact. As far as we know, this prediction is not verified. There is no evidence of a strong flow at 120 million years. So you have to be upfront and say, well, the data says this theory is wrong, but the theory is so sweet. You got to publish it anyway. So I gave this paper to Walter, and I gave it to Jonathan Levine, and showed it to them, and told them about this period. And Jonathan and Walter almost simultaneously said, what about the Anton Java Plateau? What's that? The biggest basaltic outflow of all time. In fact, I showed it to you in a previous plot. Wait, when did that take place? Let's look it up. And he looked it up. It was right where I predicted it. But wait, I said, it's not in my table. Walter looked at my table and said, Rich, you're looking at a table of continental flood basalts. Doesn't include the oceanic ones. Dumb physicist. Anyway, I feel as if I predicted this. Biggest outflow in the last 250 million years happened to be right where I said in print it would have to be, but wasn't. Of course, my paper hadn't yet been submitted, but it was so in the final paper I had to take out that prediction because it was no longer a prediction, it was a postdiction. There's the paper. This is a subject of another hour-long talk. My student Robert Rody and I found this other cycle, which is much stronger than the 26 million year cycle, a 62 million year cycle. We got this by getting the very best data and being the first ones to put it on an accurate time scale. And this was published in Nature in 2005, so it's just a year old, a year and a half old. And it indicates there's something else going on. We're trying to account for the 62 million year cycle. Best guess, it has nothing to do with the star orbiting the sun. We can rule that out. My best guess is it has to do with our motion around the Milky Way as we pass through dense regions. If we pass through a dense region every 62 million years, then that dense region will, by its effect on the outer clouds of the Oort comet cloud, the tidal gradient, as Don Morris and I showed in 1995, that tidal gradient will increase the rate of impacts. What we're seeing here is that life on Earth did not evolve with just species fighting other species, but that there's an impact, something happening from the outside. Many people believe that if not for these catastrophic events, that we wouldn't be ruled by the dinosaurs today, we'd be ruled by the anaerobic bacteria, or by maybe the aerobic bacteria, or by little microscopic protozoans, or something like that. That something that comes in and really disrupts life means you not only have to survive in the current conditions, you have to be flexible enough to survive catastrophe. And if anything has driven the development of flexibility, namely the human brain, I believe that's it. The fact that if you are adaptable, you can not only, you can get along just fine. You know, there's an advantage to being really big, like the dinosaurs, except when there's a catastrophe. Then there's an advantage to being small. The biggest advantage of all is being flexible. And we're seeing evidence of these things coming in that disrupted life. And some people think advanced life never would have formed unless we had these catastrophes happening. So here we are, all these questions. We don't know what the Nemesis is there. More we don't know. We still, every year in the paper, someone will prove that the impact 250 million years. There was something in the paper about a month and a half ago about a big crater, 250 million years old, in Australia that probably was responsible for this. And then you look at the scientific research and you find how old is that crater? And the answer is somewhere between 50 million and 400 million years old. Where did they get 250? Well, that would have to be the age if it was responsible for this. So you have to be careful. Every year, someone has published something explaining what happened then. But there's no scientific evidence for what happened then. A real great mystery. I list a bunch of the things we don't know, like what causes the 62 million year cycles. Science, to me, sometimes reminds me of an old Greek myth. The myth of Sisyphus. If you know this myth, he was the king of Corinth, and his punishment was to roll this stone up a hill. This depiction exaggerates his strength in the stone, but anyway, he had to roll it up the hill, and then as he got near the top with trouble, and it would fall down. So, anyway. Camus wrote this wonderful existentialist essay comparing this to life. I mean, here we are. What do? We work, we discover, we invent, we produce children, and then we die. You know, what's it all for? And Camus' existentialism said that's what it's all for. And Sisyphus, rolling this rock up the hill and having it roll down, and then he rolls it up again. That's life. That's happiness. When we scientists roll a rock up the hill, 2 rocks fall down. There's a lot more we don't know now than we didn't know 27 years ago. And in science, that's wonderful progress. So thank you very much.